Okay, so my Chemistry 30 class is going to be writing their equilibrium acids and bases test in a couple days, and here is a practice test I will give them full of old diploma questions. So for this first one, I'm just going over the equilibrium expression. We want to write it in. We know that it's going to be products over reactants, and any coefficient you see will be an exponent. So the answer for this first one would be D. So we have products over reactants and then those coefficients. The second one is showing that you know what you're including and what not to include. So when you're looking at the expression, you do not include solids and you do not include pure liquids unless every state within the expression is a liquid. So in this case, it's still products over reactants. Our answer would be A, to just have that because we're not including anything else. Looking at the next one, this is showing that we have that idea that we know about shifts. So because we don't include solids or pure liquids in the expression, we actually would not include this carbon. So there is a difference in moles. There's 1 mole on the left and 2 moles on the right. So when we're looking at what would favor the maximum yield of carbon monoxide, we want to be able to shift to the right. So to do that, to shift to the right, because that has a side with more moles, you would move to the side by increasing your volume or decreasing your pressure. The other way to do that with the heat is that you would want to take heat out of the system because then the equilibrium would shift to replace it. So the one that would match that would be B. Lower the temperature, so you shift to replace it, and low pressure, so you shift to the side with more moles. Looking at the numerical response number 4, we are taking a look at our system. We have some colors present, and we also still have an unequal amount of moles. So 2 on the left, 1 on the right. So when we're going through how we can shift to make the mixture dark brown, that means we want it to shift to the left. So let's go through that. Increasing the volume. If you increase the volume, you move to the side with more moles. So that would definitely work. So number 1 would be one of our answers. Not number 2 because we would shift away. Decrease your temperature. If we decrease the temperature, you would shift back to replace it. So that won't work. Increase your temperature, you shift away. So that would work. So number 4. Addition of a catalyst. Catalysts do not shift equilibrium. Decrease in pressure would shift to the side with more moles. So that would actually also work. And so that one. Decrease in N2O4, that's the side. If we took it out of the system, you would shift to replace it. So that will not work. Increase N2O4 would make you shift away. So that will work. The last one being 8. So this was 1, 4, 6, 8. Looking at number 5, which of the following would increase the equilibrium concentration of NO? So we want to, in this case, shift to the right. So the first one, if we look at decreasing the volume, we need to look at the total amount of moles. So there's 9 moles altogether on the left-hand side and 10 on the right-hand side. So if you decreased the volume, you'd move to the side with less moles, which means we would be shifting away and not towards the NO. So that one would not work. Increasing the temperature, if you increase your temperature, you shift away. So that one also would not work. Adding NH3, if you add it in, you shift away. So that would shift to the right. So that would work. So number 5 looks like it's only number 3. Looking at number 6, it tells us that we put in 1.2 moles per liter of each solution. This is essentially an initial amount. So this is going to be an ice question. So if I were to set it up, just have more room up here. The A plus B in equilibrium to give you C plus D. I'm told I have 1.2, so just setting up ice initially to start of A and B, and we could assume there's no products. Then for the change, based on the mole ratio, subtract 1x, subtract x here, that was weird, plus x, and then fill in by adding your column, so 1.2 minus x, 1.2 minus x, x, and x. If it tells you the equilibrium concentration of D is 0.60, at equilibrium, D equals, so X will equal 0.60. Now we can plug in every X value to figure out the equilibrium concentration of the others. Because it's asking us for A was 1.2 minus X, you would do 1.2 minus 0.6, and that will also equal 0.6, which is C. Question number 7 is asking us for the equilibrium constant, giving some concentrations. So you'll need to start by writing in the equilibrium expression. So we'll have products over reactants, and then just that reminder, if you do have a coefficient, that becomes your exponent. So now that we have it written out, then you're going to plug in your values that are given. So the concentrations, so we have 0.025 times 0.04 divided by 0.084, and this value would be cubed. Putting that into your calculator, and with 2 sig digs, you'll see your answer is 1.7. Our next one is telling us at a certain temperature, we have an equilibrium constant of 3.86. And then looking at this, it looks like we have another ice question. So it's placed into the flask. So if I'm setting this up with ice, I would have the original amount 0.560 of H2, and then the same amount, so 0.560 of CO2. And then to begin with, we would have no products. Then the mole ratio, so subtract x plus x plus x, and then filling in our column. Minus x, 0.56 minus x, x, and x. Now, we did all this work, but the part at the equilibrium, that is what will go into the Kc expression. So if I put in the Kc expression, it's going to be my products over my reactants. So it'd end up being H2O times CO2, or just CO, over H2 times carbon dioxide. So now I plug in those values. I have my Kc is 3.86. I have H2O is x, and the carbon monoxide is also x, so that would be x squared. Over each of these are both 0.56 minus x, and that is squared. So I'm going to do the math and solve for x. You would do that by taking the square root of both sides to cancel out the squared, multiply that denominator up, isolate x, and you would do all that work and find out that x equals 0.371, and it's asking the equilibrium concentration of CO, and CO was my last x value, and it was just x, so that would be your answer, is B. Okay. Moving on to question number 9, we have some information of an equilibrium system. And then it's just, once again, asking us the equilibrium constant. So based on that system, always Kc, products over reactants. So C6H5, CHCH2 times H2 divided by C6H5, CH2, CH3. So we don't need any exponents because we have only coefficients of 1. Once we've set it up, the expression, then you can go ahead and plug in those concentrations, put everything into your calculator, and we should see the number 2.58 as your equilibrium constant. Okay, looking at number 10, it is a continuation question with that same reaction we were looking at. And then it does ask, if you cooled the system, what would happen to the equilibrium constant? So cooling the system would have it shift to the left, making more reactants. Now the reminder is temperature is the only thing that can affect Kc. So any other shift would not change Kc, but because it's a temperature change, we are shifting towards reactants, and doing that would lower your Kc value, right? More reactants, Kc's lower, higher products, Kc's higher. So it would lower the Kc value, and then asking about the concentration of C6H5CHCH2, that would be this one here. If you are shifting to the left, that means your product had to be used up to make reactants. So your product would have to decrease. So we're going to have the answer here be D, decrease and decrease. Number 11 is giving us a graph, and it is showing the concentration of that C3O positive ion changing, and it's slowly being used up. So asking about the stress of what's happening at time t, It's definitely not an addition of HCl because that would directly add that to the system. And instead of seeing that gradual line, you would see that spike and then it being used up. But that spike's not happening. With B, if you're decreasing the temperature, you would shift towards. So a decrease in temperature would actually cause concentration to increase, not decrease. The addition of NaCH3COO, that would be adding this ion in, which would shift the system to the left. So that would slowly use up the hydronium ion. So it looks like the answer is C. And the last one, adding or increasing the volume, you have the same amount of moles on each side, and there are no gases, so a volume and a pressure change wouldn't affect the system. So the answer definitely is C here. Question number 12, which of the following applies to chemical equilibrium? So this is knowing our 4 points. They're not all listed, but just knowing them. So forward and reverse reaction rates are equal. That's true. Equilibrium can be achieved from either direction. That is true. Macroscopic properties are constant. That is true. So all of these would be true. Number 13, looking at our equilibrium system, which graph would happen or will represent what happens when HI is removed from the system. So if it is being removed, you definitely have the drop, which we're seeing in all of these graphs. But what it wants us to see is that once it's removed, you are going to take it out and we are going to shift to replace it, but you never reach the starting line. So in terms of the starting concentration, this one is right back there. It's not going to be this one. It's always going to be a little bit lower. So the answer here is B. It's never going to be above it. And this last one's just odd. So the answer here is B. We are taking it out of the system. It's going to shift to try and replace it, but it will never replace it back to its original line. Question number 14 here. The hydrogen phosphate ion can act either as an acid or a base based on Bronsted-Lowry. In which of the following reactions is our HPO42 acting as a base? If it's acting as a base, it is accepting a hydrogen. So you can, just looking at a few of the other ones, can definitely rule out this one. You're not going to react it with a base. You can rule out D. And then take a look at what's happening in reaction A. We're adding in hydronium. That is definitely an acid being added to the base. So it looks like the answer is A, but you can double check the last one. If it was acting like a base and we moved this to the left, we would not be losing the hydrogen over here to make this, and we wouldn't be forming hydronium. So the answer definitely is A. Question number 15, all of the following are acid-base conjugate pairs except. So to be a conjugate, you're a difference of just one hydrogen. So this works, this works, this does work, and this last one does not work because it's a difference of two hydrogens, not one. Question number 16, we have an aqueous solution of this compound, which is a weak base. They give us the Kb and ask us the pH. So if we're dealing with Kb, we can use a formula. The hydroxide ion squared is going to be divided by the concentration of the weak base minus the hydroxide ion. So what we talked about in class is that if you know the hydroxide concentration, you use it. If you don't have it, you could ignore it because this is based on the ICE charts. So we can fill in our information. We know the Kb, so 1.1 times 10 to the negative 8. That is going to equal the hydroxide ion squared divided by the concentration of the weak base, which is 0.1. We're going to isolate the hydroxide, so multiplying the weak base up, taking the square root. Once you do that, you'll have the concentration of the hydroxide ion, which allows you to find POH. And then if you have POH, you can then find pH by taking it away from 14. So you do all of that work and you will see that your answer is C. So moving on to question number 17. This one, the position of equilibrium lies to the right. If your reaction is lying on the right-hand side, that means what's happening on the left-hand side is a bit stronger because it's pushing your reaction to the right. It's making more products. So asking what is the stronger acid, you first want to identify your acids. So in the reactant side, this one here is your acid. You can tell because a hydrogen is going over to the NH3. And on the right-hand side, we have NH4 positive as an acid because your hydrogen, oh, I said that backwards. Sorry, this one is your acid because your hydrogen is moving over to the NH4. So with that, because we're looking for the stronger acid to push the reaction to the right, our answer would be the N2H5. So your answer is A. Okay. Our next one, we have a titration. We're looking at what's in the flask. We have that pH curve. Number 18 says, which pair of aqueous solutions would represent this titration? Now, the fact that you are starting a little bit over, well, it looks like you're between 2 and 4, so that would be 3. Any pH between 0 and 2 would be a strong acid. After that, it's weak. So this shows you're starting with a weak acid, and anything above 12 would be a strong base. So you're titrating a weak acid with a strong base. So now going through your options, and it only has one equivalence point, so it would be mono product. So it's not this first one because that is strong. It's not the second one because we have some weak bases in there. It's going to be this last one because we have your weak acid with your strong base. So this answer would be D. Question number 19 asks, where is your buffer region? Buffer regions only exist if you have a weak acid or a weak base present. You have a weak acid present, so your buffer region would be that area that's resisting that change in pH until it can't. So that looks like this is between 4 to 16. Number 20, which pair of aqueous 1 molar solutions could be chosen to prepare a buffer? So to be a buffer, you need a weak acid with its conjugate base, and a weak base. So again, you differ by 1 hydrogen. So it cannot be this first one because HCl is strong. It could be the second one because that is a weak acid with its conjugate base. And it also could be this last one for the same reason. So it looks like here our answer is number 2 and number 3 only. Okay, so there's lots going on in this next question. It's giving you an acid that's not on page 8-9 of your data booklet. So I just took a screenshot of page 8-9, but it gives you Ka value. So if you have a Ka value of 1.4 times 10 to the negative 3, it's going to be around this area. Okay. When it asks us to compare it to the carbonic acid, so carbonic acid, if you take a look at what we have here, is down here, carbonic acid. It would be a stronger acid because it would be placed higher up on the table, right? And we know for acids, it starts off strong and as you go down, it gets weaker. And then comparing it to the ion, the carbonate ion, which would be this one down here, in terms of a base, it would be, which one do we have here? 21 is A. So it would be a weaker base. Oh, because the base part of the conjugate is higher up than the carbonic ion. So it's a stronger acid with a weaker base. Looking at number 22, you have the hydrogen phosphate ion, and then it's asking for the Kb. So I just take a look at where the hydrogen phosphate ion is as a base, and you have the Ka value, and we just want to remember that if you have a Ka and you want a Kb, you just take the Kw and divide it by the Ka. So the Kw is 1.0 times 10 to the negative 14. The Ka is what we're going to fill in. When you're doing this, just make sure you have the denominator in brackets, and you should see your answer here would be 1.61 times 10 to the negative 7. So if we're filling it in with our scientific notation, it'd be 161 and 7 because your exponent is that D value. Question 23. If your pH solution changes from 3 to 5, then the hydronium ion will change by a factor of blank, and the hydroxide ion concentration in the solution will blank. So for this one, this is a bit more of Chem 20. Every time you move up the pH scale, so going from 1 to 2, your hydronium ion changes by a factor of 10. So if you're going in here, if you're going from 3 to 4, that would be by a factor of 10, and then 4 to 5 would be another factor of 10. So altogether, multiplying, that's going to be a factor of 100. And then when you're talking about the hydroxide ion concentration, if you're moving up the pH scale, right, so from 0 to 14, if you're moving up, you are making more hydroxide. So looking for The answer, we know it's going to be the 100, and your hydroxide ion has to be increasing. Our very last one here, we have our equilibrium system of hydrogen sulfide gas, and it's asked here what our hydronium ion concentration is and what is the pH of the system. So in this case, you can look up the Ka value from your data booklet. So if it's not given to you, look it up. If you have enough information to solve for it, you do want to solve for it. And that is 8.9 times 10 to the negative 8. So when you are looking at the Ka formula, it is the hydronium ion squared divided by the concentration of your weak acid minus hydronium. So just like that question we did with hydroxide, if you're finding it, you could ignore it in the denominator. If you have it, use it. So in this case, we want to find it because we have Ka, we have the concentration of the weak acid. So we're going to find the hydronium concentration. And when you do that, you'll see the answer is 6.7 times 10 to the negative 5. Having the hydronium ion allows you to solve for pH, and then taking it away from 14 allows you to find pOH. And so looking at these two and then following these steps, your answer is D. Now my dogs are going crazy, but good thing this is the end. I hope that helps. If you have any questions, please let me know in the comment. And if you did find this helpful, please subscribe. Thanks for watching.